ನಾನು ವಿಡಿಯೋ ಆನ್ ಮಾಡ್ಬೇಕಾ?
ಅಲ್ಲ, ಇಫ್ ಯು ನೀಡ್ ಮಾಡ್ಕೊಳ್ಳಿ ಸರ್, ಏನ್ ತೊಂದರೆ ಇಲ್ಲ ಸರ್.
ಓಕೆ.
So good afternoon, sir.
Very good afternoon, sir.
ಸೊ ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಅರುಣ್ ಇಸ್ಲೂರ್ ಸರ್ ಅವರು ಕೆಮಿಸ್ಟ್ರಿ ಆಫ್ ಕಾರ್ಬೋಹೈಡ್ರೇಟ್ಸ್ ಹೈಡ್ರೋಕಾರ್ಬನ್ಸ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು ಅವರನ್ನು ನಮ್ಮ ಅಕಾಡೆಮಿಗೆ ಹೃತ್ಪೂರ್ವಕವಾಗಿ ಸ್ವಾಗತಿಸುತ್ತಿದ್ದೇವೆ. ವೆಲ್ಕಮ್ ಟು ಟುಡೇಸ್ ಸೆಷನ್ ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್, ತುಂಬಾ ಧನ್ಯವಾದಗಳು.
ಸೊ ತಮ್ಮ ಬಗ್ಗೆ ಕಳೆದ ತರಗತಿಯಲ್ಲಿ ವಿಸ್ತೃತವಾಗಿ ನಾನು ಕಿರುಪರಿಚಯ ಮಾಡಿಕೊಂಡಿದ್ದೀನಿ ಸರ್. ಸೊ ಸಮಯಾವಕಾಶ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ ಸೊ ನೀವು ನೇರವಾಗಿ ಉಪನ್ಯಾಸಕ್ಕೆ ಜಾಯ್ನ್ ಆಗ್ಬೋದು ಸರ್. ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಅಧ್ಯಕ್ಷರಾದಂಥ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ಅದೇ ರೀತಿ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯವೂ ಪ್ರತಿನಿತ್ಯವೂ ಸಲಹೆ ಸೂಚನೆಗಳನ್ನು ನೀಡುತ್ತಾ ಬಂದಿರುವ ಡಾಕ್ಟರ್ ನಮ್ಮ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಂತಹ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ಹಾಜರಾಗಿರ್ತಕ್ಕಂಥ ನನ್ನ ಎಲ್ಲ ಹೆಚ್ಚಿನ ವಿದ್ಯಾರ್ಥಿಗಳು ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿ ಮಿತ್ರರಿಗೂ ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ಓವರ್ ಟು ಯು ಸರ್.
Okay. Thank you, sir. Very good afternoon to all of you. First of all, I take this opportunity to thank Professor Ayyappa sir, as well as Dr. Ramesh sir, as well as the entire KSTA team for giving this wonderful opportunity to me to interact with the 11th and 12th standard students of our state. And for the next 55 to 60 minutes, I'll be talking about a topic called carbohydrate, chemistry of carbohydrates. Without making any delay, let me share the slides. I hope my slides are visible.
Yes, sir, visible, sir.
Okay. Yeah, thank you. Okay, in this particular picture, if you look at this picture, you can see colorful foodstuffs. In the first picture, the potatoes, and then rice is there, wheat is there, pasta or the noodles, and then a different type of the cereals. And in the second picture, you can see the colorful ice candies, right? And then one more pharmaceutical compound you can see in one of the picture, which is nothing but actually sorbitol. And in our day-to-day, again, the useful item that is a toothpaste, or some of the pharma compound which is antibiotic, that is streptomycin is there. And you can see one more picture where high fructose corn syrup, this is actually short form known as HFCS. It is commonly used as an adulterant for the honey. So these are all the some of the colorful pictures. It shows one or the other way they are nothing but the basically composed of the carbohydrate molecules. You may ask me, what is the importance of studying the carbohydrates, or why these carbohydrates? What are these carbohydrates? Why we have to study? So carbohydrates are basically, these are nothing but the sources for energy which is required for the survival of any of the organism. ಯಾವುದೇ ಒಂದು ನಮ್ಮ ದೈನಂದಿನ ಕಾರ್ಯದಲ್ಲಿ ಯಾವುದೇ ಚಟುವಟಿಕೆಗಳನ್ನು ಮಾಡಬೇಕಾದ್ರೆ ನಮಗೆ ಒಂದು ಶಕ್ತಿ ಬೇಕು. We need energy, and the energy that will come from the fuel, which is nothing but the carbohydrate itself. Or the as a chemistry wise, we can give the different definition also. I'll come to that in the latest slide. Here, in the first, this colorful slide, I have presented one pharmaceutical compound, which is nothing but the sorbitol. And this sorbitol, actually, it is used as a laxative. It is used as a laxative in the pharmaceuticals, or even in the toothpaste. You may be thinking that the toothpaste, most of the 95-98% of the toothpaste which are available in the market, these are sweeter in taste, right? You may be thinking that the sweetness in those toothpaste, it is because of the regular sugar. If you think so, you are absolutely wrong. There actually, in any such toothpaste, the sweetness, the sweetener which is used is that is a sorbitol molecule. And sorbitol is, later you'll see the chemical structure also. This sorbitol is it's a carbohydrate molecule. It is sweeter in taste. Then what may be the why we cannot use the regular sugar in the this toothpaste? This question might have came in your mind, right? If we use definitely, if we can use the regular table sugar. However, the thing is, it can again it may be responsible for decaying of the teeth. The purpose of using the toothpaste is to prevent the tooth decay. But if you use a toothpaste which is composed of table sugar as a sweetener, then it can enhance the tooth decay. So the other sweetener, which is nothing but the sorbitol, and this sorbitol, it will not be undergoing any sort of decomposition or decay by the bacteria or microorganism. So that is why sorbitol is used in our toothpaste. Similarly, many of the expectorants, ನಮ್ಗೀಗ ಕೆಮ್ಮು ಅಥವಾ ಆದಾಗ ನಾವೇನು ಡಾಕ್ಟರ್ ನಮ್ಗೆ ಏನು ಒಂದು ಔಷಧಿಯನ್ನ ಕೊಡ್ತಾರೆ, ತುಂಬಾ ಸ್ವೀಟ್ ಇರುತ್ತೆ. ದ ಎಕ್ಸ್ಪೆಕ್ಟರೆಂಟ್ ಆರ್ other type of the pharmaceutical tonics which are generally sweeter in nature, and in which also the sweetener is a sugar is not at all the table sugar. I mean to say the table sugar, that is not at all the actual sweetener which is used. What happens is, if we use in such pharmaceutical compounds or in such preparations, if we use the table sugar, then that may responsible for what about the patients who are with the blood sugar or with the diabetic patients. So again, that may enhance the diabetic condition. So again, we have to use such type of the sweetener which cannot enhance our any sugar level at all. That is nothing but the sorbitol. Or in market, you might have seen different type of the energy drinks which are available, which are free from the table sugar, but the sweetener is because of this sorbitol molecule. Okay. And the high fructose corn syrup, this is actually, it is prepared from the corn itself, and it has exactly the similar look and almost the same taste as that of our natural honey. So this is a very cheaply available per kg. This can be obtained about 30 to 40 rupees or even lesser than that. And this can be easily adulterated in any of the honey, and you cannot distinguish even by the chemical test. Because in the natural honey, about 50 to 60% of fructose molecule which is present. And this high fructose corn syrup, it is completely made up of, it contains only the fructose. If the honey would have been adulterated by regular sugar solution, sugar syrup, or the what you call the jaggery solution, in that case, the adulteration that can be easily identified, because it is basically composed of the table sugar is nothing but it is a sucrose molecule that can be easily, chemical testing easily one can identify. But the natural honey is also containing the about 55 to 60% of fructose molecule, and this high fructose corn syrup is also composed of fructose molecule. The the honey by adding this one, nobody can identify. So that's why nowadays the honey which is being in the market with the famous brands also, they are adulterated by, as a chemist, I can say that they are adulterated by high fructose corn syrup. Okay, so this is the, just I wanted to tell what are the importance of these carbohydrates in our day-to-day life. Let us go to the chemistry of these things. So the introduction wise, the word carbohydrate, this is actually derived from their general formula CH2O N times, and that makes them seem to be hydrates of the carbon. And the terms carbohydrate and the saccharides, these are very much closely related. The carbohydrate, actually, this particular terminology is used in the last 50, 60 years or so. But before that, before 50, 60 years back, the term saccharides were commonly used for these to define the carbohydrate. But nowadays, the term carbohydrate is not at all, it is not at all recommended in the scientific way. This is not at all recommended, because the term saccharide, it refers to the sweet. Of course, most of the lower members of the carbohydrates, they are sweeter in nature, but there are a large number of higher members of the carbohydrate which are not at all sweeter in nature. So in such case, the term saccharide, it is not a correct one. So that's the reason nowadays the word carbohydrate is, this is chemically or scientifically, this is the correct word. And this is the most abundant carbohydrates, which are nothing but the polysaccharide. So for example, in case of the human being or any other vertebrate animals, where the reserve food, that is in the form of the glycogen. I'll come to the structure of that later. And the glycogen, it is an example for the polysaccharide molecule. Or if you consider the plants as an example, consider any plant. In plants, the reserve food, that is in the form of the starch. And this starch, whenever the plant requires, this starch will be converted into the glucose, and that will be utilized for its biochemical reactions. So the most of the carbohydrates, abundantly available carbohydrates, they are nothing but the polysaccharides. And most important carbohydrate in our body for the human being, which are nothing but the glucose. All this chemical structure we are going to see later. Now, how to define a carbohydrate? Whenever I ask this question to, even at the post-graduation level also, they give the definition as the compounds which are containing carbon, hydrogen, and oxygen. So if you give that type of definition, then it is completely wrong. Because we can give many of the cyclic compound which are containing the carbon, hydrogen, and oxygen, but they are not at all carbohydrates. So please don't give the definition, because this is also the very older definition where carbon, hydrogen, and oxygen containing compound. So don't give that particular definition. So as per the modern chemistry, carbohydrate definitions are nothing but they are polyhydroxy aldehydes or polyhydroxy ketones, or compounds that yield these derivatives on hydrolysis. That means when you hydrolyze any such compounds, if they give polyhydroxy aldehydes or polyhydroxy ketones, then they are nothing but the carbohydrate. So this is the correct scientific definition of the carbohydrates. What is the importance of these carbohydrates? Few of the points already I have mentioned in the beginning only, in the first slide. These are widely distributed in the nature among the plants as well as the any living organisms. And these are the key intermediates of metabolism. That is nothing but the sugars, varieties of the sugar. So sugar means, you please don't misunderstand that only the table sugar what we are using for making tea or for our any of the regular diet. So in the carbohydrate, any of the molecules, they can nothing but they are the sugars. Scientifically or chemically, the table sugar, its chemical name is nothing but that is the structural components of these plants, that is nothing but the cellulose, and the central to material industrial products like the papers. Again, the paper is the paper which we are using. This is basically made up of it's a cellulose material or varieties of the fibers. So these are all industrially important materials. So these are also basically from the carbohydrate. Not only that, even in the pharmaceuticals, where the sorbitol, which I have mentioned, or the streptomycin, or the heparin. So many such examples are which are basically carbohydrates in nature. They find a lot of industrial application, particularly in the pharmaceutical field. And key component of the food sources like the sugars, varieties of the sugar. It need not be only the table sugar, or it may be the flour, rice flour or wheat flour or ragi, whatever flour you mentioned, or the vegetable fibers. Basically, they are nothing but the carbohydrate. So we can say that without carbohydrate, our life is incomplete. This is one such example. As I mentioned, the glycogen, which is the reserve food in the case of the any vertebrates, including the human. So this glycogen, this is actually a polysaccharide molecule. Whenever during starving condition, this polysaccharide or the glycogen molecule, it will be liberated in small quantity or in the required amount, and it undergoes the hydrolysis in the body, and this glycogen, part of the glycogen, it gets converted into D-glucose or simply as a glucose. That is how even during the starvation also, we'll get the energy that is nothing but through the stored polysaccharide molecule, which is nothing but the glycogen. Similarly, in the case of the plants, the starch is a reserve food, and whenever required, the starch gets converted into glucose for the plant. And functions of these carbohydrates, as some of the points have been already discussed, like as an energy source or as an intermediate in the metabolism or from the storage form of the energy, structural components, fibers, constituent of the nucleotide, the ribo detoxification, etc. Even in the case of the DNA or in RNA, that is, they are nothing but the nucleic acids, deoxyribonucleic acid or the ribonucleic acid, where also the structural component is one of the sugar which is present, that is nothing but the ribo sugar. So that also shows that the carbohydrate is part of our life. So some of the terms, whenever you study the carbohydrate chemistry, following few terms are quite common. That is aldose. It refers to a carbohydrate which contains aldehyde group. Ketose or keto sugar, which is nothing but a carbohydrate which contains a ketone in it, C double bond O group. Triose is nothing but a carbohydrate which is containing the 3 carbon atom. Similarly, 4 carbon atom, which are the tetrose. Pentose is for the 5, or ketohexose, which is nothing but the 6 carbon atom containing ketone group. So on. Now let us come to the classification of this carbohydrate. They have been classified mainly in the broadly. They have been classified in the following 3 categories. So one is monosaccharide, second one is oligosaccharide or the disaccharide, and the third one is polysaccharide. So monosaccharides are those when they are which are nothing but the most simplest carbohydrate molecule. They won't undergo further any sort of hydrolysis, or most simplest sugars which are nothing but the monosaccharides. Disaccharides are those when they are hydrolyzed, they give 2 numbers of the monosaccharide units. Oligosaccharides are those they give 3 to 9 number of the monosaccharide. And the polysaccharides are those they give on hydrolysis, they give 10 or more than 10 numbers of the monosaccharide units. So some of the examples I have listed here, and based on the functional group, if aldehyde is a functional group, they are nothing but the aldo sugar. For example, glucose. And if there is a functional group is ketone in nature or ketose, then fructose as an example, where C double bond O group is present. Similarly, based on the, in case of the disaccharides, maltose or lactose or sucrose. Sucrose is our table sugar. That is an example of the disaccharide only. Lactose sugar, it is present in the any of the milk of the any of the animals. So that contains lactose sugar. The maltose, again, it is present in the malt or in the germinating cereals, where actually the maltose which is present. Similarly, the polysaccharide, uh, there are again homopolysaccharide as well as heteropolysaccharides. That means if it gives on the hydrolysis of a starch, if it gives only one type of the monomeric units, I mean similar type of the monosaccharides, then they are homopolysaccharide. For example, starch. When starch undergoes the hydrolysis, it gives only the glucose molecule. Glucose is a monosaccharide here, so it gives only one type of the monosaccharide. Similarly, the heteropolysaccharides are those, it gives two or more than two different type of the monosaccharide units on hydrolysis. Say for example, hyaluronic acid. When this is hydrolyzed, it gives the, in this particular case, the formation of the more than two different type of the monosaccharide units will be formed. The monosaccharide example is the glucose. So this is nothing but when it is hydrolyzed, it won't further undergoes the any sort of hydrolysis. That means it's the most simplest in nature. Many examples we can give here. Already I have mentioned few of the example. So the monosaccharides are subdivided into different groups. So depending upon what type of the functional group is there, whether aldehyde or ketone, they have been subclassified as aldoses or ketoses. And depending upon the number of the carbon atoms they possesses, if there are 3 carbon atom, 4, 5, 6 or 7 or more than that, depending upon that, triose, tetrose, pentose, hexose, heptose, etc. So these are few typical examples. Then the next one, the triose, some of the example for the triose are which are nothing but the glyceraldehyde, then which is actually the most simplest sugar. The glyceraldehyde is considered as most simplest sugar. Similarly, the tetrose molecule. Similarly, the tetrose molecule, where D-erythrose is the example. Then the next one is pentose, which is actually the D-ribose. And this particular D-ribose, this is present in the ribose sugar. It is present in the nucleic acid, which I have already mentioned. Or the D-glucose or the hexose, the galactose molecule, the glucose, fructose, galactose, mannose. So all these are example for the 6-member carbohydrates. Then the oligosaccharides are actually, they are nothing but they contain 2 to 10. It gives on hydrolysis, it gives 2 to 10 number of the monosaccharide units, and they are joined together by specific bonds which are called as glycosidic bond. And these are on hydrolysis, they give 2 to 10 molecules. They may be the same type of molecules or different type of the molecules, depending upon what type of the disaccharide it is. And they are further again subdivided into, based on the number of the saccharide units, they have been further subclassified as disaccharide, trisaccharide, tetrasaccharide, pentasaccharide, etc. And the classification of this disaccharide, classification of the disaccharide, this is actually the maltose, that means the number of carbon atoms are 2. Examples like the maltose or the lactose or the sucrose. Then the type of the monosaccharide. Say when our table sugar, the normal sugar or the table sugar, when it is subjected to hydrolysis, it gives glucose and fructose molecule. The same one, when the lactose molecule, that is the lactose is a it's a carbohydrate present in the milk. So when this is hydrolyzed, it gives glucose and the galactose molecule. Similarly, the maltose, when it undergoes the hydrolysis, it gives only the glucose molecules. See the diversity among these disaccharide or trisaccharide or the all these carbohydrate molecules. The polysaccharide, the term polysaccharide, this is nothing but when they are, these are the carbohydrate, when they are subjected to hydrolysis, they give 10 or more than 10 monosaccharide units. 10 or at least 10 units or more than 10 units. If it is below between 3 to 9 number of the monosaccharide means they are the actually the oligosaccharides. Let me give one interesting example here. So here some vegetable soup you might have seen in the restaurants also. Commonly this you might have observed. The soup which is served in the restaurant, initially it is very thick. When it is very hot, it will be very thick. If you, after few minutes, when it becomes lukewarm or when it becomes cold, it will be watery. It loses its thickness. Have you observed this? If not, in the next time, whenever you are consuming the soup, please observe this particular one. Here, actually, what happens is while making the any such type of the, whether it's a vegetarian or non-vegetarian type of the soup, where the starch is starch powder is which is commonly used. And starch, it is a polysaccharide molecule. It is composed of, one is amylose molecule and another unit is amylopectin is another unit which is present. And this amylose, it is easily water soluble. Whereas the amylopectin, this is a highly coiled structure. You can see here, the first one is it's a linear one, whereas in the second one, it's a coiled structure. It is having several branches. And the solubility of this one is very poor. But in hot water, initially immediately it won't undergo any solubility or it won't undergo any dissolution. But after a few minutes, some of the molecules of the amylopectin, it get dissolved in the hot water. Since the amylose is completely dissolved and some part of the amylopectin it dissolves after 5, 6 or 7 minutes or so, by that time most of the amylopectin which get dissolved. So because of that, there's any these type of the soups which are served after once it attains the lukewarm or once it becomes attains the normal temperature, it will be like a watery or it will be more liquid. But when it is served hot, it will be very thick in nature. The polysaccharides already I've completed. These are the some of the typical examples, homopolysaccharide as well as the heteropolysaccharide, where under the homopolysaccharide starch is there, it only gives the glucose. Glycogen, it also gives only the glucose, or the dextrin, this also only gives the glucose. Whereas in the heteropolysaccharide, agar or the pectin or the glycosaccharide, they give different type of the monosaccharides. Now let us see the structural, something more chemistry. Now after this classification and different examples, different lively example, let us move to the structural as well as the functional relationship of these monosaccharide. So this is the structure of the glucose. Now we'll study its structure in detail. So glucose, it's the most important physiological and biomedically also important monosaccharide. It can be represented in the straight chain structure, which is nothing but this one, the open chain structure or the straight chain structure, or ring-like structure. You can see it later, ring or the cyclic structure. And also, apart from that, boat and the chair form. In three different forms, the structure of the glucose can be represented. So this is actually the straight chain structure. Here you can see there are totally 6 carbon atoms, and there is arrangement of a H and the OH in a definite sequence. And then at the terminal one end, there is a aldehyde group. So it is a aldohexose. Glucose is an example for the aldohexose. And at the other side, there is a free CH2OH group is. Now, let us see the cyclic or the ring-like structure of the glucose molecule. And this particular ring-like structure or the cyclic structure, this was actually proposed by a chemist by name Haworth. And as a honor to this chemist, the name of the such a type of cyclic structure of the glucose or any such type of the carbohydrate, which is termed as Haworth representation or Haworth projection. So you might have already came across this particular terminology in your 11th or in the 12th standard textbook. Haworth representation, or this is called Haworth projection. Let us see how this particular Haworth representation or Haworth structure can be, how this can be written. You see in the first one, there is an open chain structure of the D-glucose is there. Now, if you can number this one, the CHO, the top carbon atom, that will be numbered as 1, then subsequently 2, 3, 4, 5, and the 6th one, right? Now here, the intramolecular cyclization, intramolecular, that means within the same molecule. Inter is refers to the within the two different one, but intra which refers to the within the same given molecule. So within this molecule, 1 and 5th position, there is undergoing, it is undergoing the intramolecular cyclization. You can see the first carbon atom and the 5th carbon atom, it forms a intramolecular cyclization, and as a result of that, the alpha D glucopyranose ring structure, this we can propose. And then while writing the representing the Haworth structure, you have to in chemistry again, organic chemistry, you recollect the structure of the pyranose. It's a heterocyclic compound, cyclic compound, which contains one heteroatom. This is nothing but the oxygen. So the structure of the pyranose you recollect, and while writing the structure of the any this Haworth representation for any such carbohydrate, the common strategy or the principle one need to remember is the structure of the pyranose ring structure. It should be written horizontally, and oxygen should be on the right and upper side. The ring oxygen, it should come right as well as upper side. If you look at this structure, you can clearly understand the oxygen in the ring that is been taken on the right upper side. So that should be the main skeleton should be presented in that way. And then you come to the again the open chain structure, or in the alpha D glucopyranose, that is Fischer structure, which is in the second structure. You again come to that. Whatever the OH groups which are present on the right side, if you consider the first carbon atom, see on the left side there is a H, and on the right side there is a OH. So the right side OH, it should come in the Haworth representation, it should come below the plane. Just see now the second oxygen atom, the second carbon atom, where the OH is on the again right side. So here again in the last Haworth structure, the second carbon atom, the OH is below the plane. In the third carbon atom, the OH is on the left side. So in the Haworth representation on the third carbon atom, OH, whatever is on the right side, it should come below the plane. Whatever is on the left side, it should come above the plane. So this is how one can represent the structure of the any carbohydrate in the Haworth structure. So if any doubts, any clarification, you can interrupt at any moment and you can try to get it clarified. I know many of you are observing through the YouTube. You may not be able to directly interact, or those who are on the live stream, they can directly interact. And similarly, the another one is a fructose molecule. And this fructose is an example for a keto sugar, because you can see here the functional group is, in the previous one it is a CHO, which is a aldehyde, but now the C double bond O, which is nothing but the keto group. So fructose is a keto sugar. Here what happens is 2,5 intramolecular cyclization. 2,5 intramolecular cyclization. Such 2,5 intramolecular cyclization, it gives a 5-membered compound. And this 5-membered compound, this has a similar skeleton, same skeleton as that of the furanose. This is another heterocyclic compound, 5-membered compound where oxygen is one of the heteroatom. In the previous one, 6-membered compound with the oxygen atom. Now it's because of the 2,5 intramolecular cyclization, it attains the cyclic 5-membered cyclic structure. And here also the same thing. Whatever the groups OH or H which are on the right hand side of the carbon atom in the open chain structure, it should come below the plane. Whatever things which are on the left side, it should come above the plane. So this is how we can show the Haworth projection or representation for the glucose as well as the fructose molecule. And also we can also represent the chair as well as the board form. You can see here the first one, it looks like a easy chair. So this is the structure of the chair form of the glucose. The second one, it looks like a boat. So this is the boat form or boat structure for the glucose molecule. Now further we'll continue, that is the properties of this monosaccharide. Here two terminologies are important. One is isomerism, and we'll also come across with few of the chemical reactions also. Isomerism, this is nothing but the compounds which are possessing the same molecular formula, but structurally they are different. They are termed as isomers. I'll repeat again. Molecules which, the compounds which are having the same molecular formula, but structurally which are different, they are nothing but the isomers. The phenomenon of existence of the isomer, which is called as isomerism. So in case of the carbohydrate, we can propose two different type of the isomerism, mainly broadly two type of the isomerism. One is structural isomerism and another one is stereo isomerism. We'll come to these things now. In structural isomerism, same molecular formula but differ in the structure, and there is a aldose and ketose isomerism. For example, if you look at the glucose and the fructose molecule, structurally they are different. Structurally, glucose and the fructose, these are different, but their molecular formula, that is the same. Structurally they are different, but molecular formula wise, they are same. So this is aldose ketose isomerism, that is nothing but the structural isomerism. Glucose and the fructose, these are the examples. This is a structure of glucose, and another one is the structure of the fructose. The molecular formula for both these one, C6H12O6, but the structures are different. In the first one, CHO aldehyde is the functional group. In the second one, C double bond O or carbonyl group is the functional group. Now the stereoisomerism, let us see. Same molecular formula, structures, same molecular formula, structures, but differ in the configuration. The structure is also same, but their configuration is different. Similarly, the asymmetric carbon atoms which allow the formation of the stereoisomerism. The chiral carbon atom or asymmetric carbon atom. That means when a carbon atom, when it is bonded to four different atoms or group of atoms, which is called as asymmetric carbon atom or chiral carbon atom. And this stereoisomerism, it is because of the such asymmetric or chiral carbon atoms. And the types of this stereoisomerism of glucose, these are actually D and L isomerism, optical isomerism, epimerism, and another one is the anomerism. T and L isomers or T and L isomerism. So these are nothing but enantiomers of each other. Enantiomer means, suppose one molecule, we have a D, suppose the first molecule, the D-glyceraldehyde, if you hold it in front of the mirror, imaginarily just hold it in front of the mirror. So there will be the whatever its image, exactly its mirror image, but they are non-superimposable. So such pairs of compounds which are non-superimposable mirror image of each other, they are nothing but the enantiomers. So D-glyceraldehyde and L-glyceraldehyde, these are mirror images of each other, but they are not superimposable. You cannot fix them one above the other exactly, but they are mirror images. Similarly, D-glucose and L-glucose also, they are also exactly the mirror images, but non-superimposable. So these are nothing but the D and L type of the isomerism or isomers, or they are the enantiomers. Again, the same one. Next one is the optical isomerism or optical isomers. The optical activity, this is actually the capacity of a substance to rotate the plane polarized light to either the right or the left side. So some of the compounds, they have the property, thereby they can rotate the plane of polarized light either in clockwise or anti-clockwise direction. So if the light will be rotated by that particular compound towards the clockwise, then it is nothing but the dextrorotatory, or that is denoted as plus. Here small d you have to write. The previous capital D, that is actually for the enantiomers or nothing but the, while defining the, it's a configuration. But this is the small d and the plus symbol, this is actually representing the optical isomerism. So when it rotates the plane of plane polarized light towards the anti-clockwise or on the left side, then that is nothing but the levorotatory. This can be denoted as minus symbol or with the small L letter. And when these both equal amount of D and L isomers are present, that mixture is said to be racemic in nature. It's called as a racemic mixture when both plus and minus sugars are in equal amount. Then the total rotational value will be completely, it get neutralized. That is, they are nothing but they are termed as racemic mixture. I'll give you one example here. You might have all of you might have definitely tried the ice candies or ice golas which are available in market, right? And the same ice candies you might have attempted in your house also, in your residences, by preparing the uh, orange flavored or the mango flavored and keeping it in the deep freezer in the refrigerator. You might have attempted that, but in the commercial one, the texture is very soft and it's a softer in nature. The commercially available, where it is preserved for minus 10 or minus 15 degrees Celsius, but it is a somewhat soft. But the same candy which you have prepared in your residence, you might have, the texture will be very tough, very hard, right? If you have not attempted this, you please try this. Why this is so? The commercial ones are softer, whereas the residents in the residence, whatever we prepare the ice candies, these are harder. The reason is we are using in the residences, we are using the regular table sugar or the regular sucrose molecule, which is the table sugar is the common name. But in the commercial ones, they are adding the either the invert sugar or fructose in more quantity. Here, the fructose molecule is having one property. It can prevent the crystallization. It minimizes the crystallization. As there is a presence of the fructose molecule also in the commercial one, and the fructose is having the property of minimizing the crystallization. Because of that, the ice candies are much softer in its texture. That is particularly in commercial. So in your residences also, if you use the residential preparation of the ice candies, if you use the invert sugar or the fructose as a sugar instead of the normal table sugar, here also you can get the similar type of the texture. So that is the secret chemistry behind commercial ice candies. So this is a light source, and when you keep a polarizer, it filters the light and only the monochromatic beam of light. And when you keep a sample, if it rotates to the right side, then that is a dextrorotatory. If it is rotates to the left side, then it's a levorotatory in nature. Let us come to the next term, that is epimerism or epimers. So epimers are sugars which are differ with each other with the respect to a single carbon atom other than anomeric carbon. Galactose and mannose, I will come to the structure in the next slide. Galactose and mannose, these are actually epimers. You will see that only at one carbon atom there is some difference is there. Rest all things are exactly same. Just see here, the first two example, D-galactose and D-glucose. Here on the fourth carbon atom in the first one, the H and OH are inverted in the D-glucose molecule. Rest are all are same. Similarly, if you consider D-glucose and D-mannose, at the second carbon atom, there is interconversion. So D-glucose and D-mannose, these are a set of epimers. D-galactose and D-glucose, these are another set of the epimers. I hope this is clear to you. The next term is anomers or anomerism. In solution, glucose will be predominantly existing as a closed chain structure. And because of cyclization of the sugar, that means this will be anomers. This is particularly term applicable whenever the carbohydrates are in the ring structure or in the cyclization of the sugar. So in such case, an additional asymmetric center is created at the C1, which is nothing but the anomeric carbon. As a result of that, two isomers we can get. That is, one is alpha D-glucopyranose and another one is beta D-glucopyranose. You see here, alpha D-glucose and the another one is beta D-glucose. Is mutarotation. So mutarotation, so this is defined as the change in the specific optical rotation representing the interconversion of a alpha and beta forms of a D-glucose to an equilibrium mixture. That means when you prepare alpha D-glucose, its specific rotation is found to be plus 112.2 degrees. When you dissolve that one and when you keep it in the water for a few minutes, after a few minutes, it will reaches to that stage where its specific rotation will be plus 52.7 degrees. Similarly, the pure beta D glucose, it has a specific rotation of plus 18.7 degrees. So when you keep its solution, when you prepare its solution and when you keep it aside, within few minutes, it will come to the specific rotation plus 52.7. So this particular change in the specific optical rotation, which is nothing but the mutarotation. So each of the carbohydrate that has different mutarotation value. This is particularly for glucose molecule. So this is here, the glucose, you can see alpha D glucose and the beta D glucose. Let us come to the chemical properties of these monosaccharides. So some of the important chemical properties of the monosaccharides are the furfural formation. Furfural is it's a chemical compound. So glucose can be converted into furfural, or enolization, which is possible, or the oxidation is possible. Reduction reactions can be carried out. Oxygen formation can be carried out. So by these different type of the chemical reactions, we can get different useful industrial product for the industrial application. It may be in the pharmaceuticals, or it may be for the paper industry, or it may be for the other healthcare or the beauty industries. So where different type of the products can be obtained by carrying out different set of chemical reaction on the glucose itself. There are hundreds of such monomers or the monosaccharides or the disaccharides are there. So if you carry out varieties of such reactions, we can get several hundreds of such other type of the industrially useful products. Furfural, this is actually sugar when treated with a strong mineral acid like either sulfuric acid or HCl or with the nitric acid, the formation of the furfural will be possible. It's a liquid, it's a colorless liquid. They undergoes the dehydration, loses 3 water molecules to form the furfural derivative. And this is the basis for the following reaction, that is Molish test as well as Selvinov's test. So these are actually tests for the glucose. And this is actually the color change in the case of the test of the glucose. The tautomerization or the action of alkalis. So when glucose is kept in alkaline solution for several hours, it undergoes the isomerization and it forms D-fructose as well as D-mannose. And this actually results in the formation of common intermediate, which is the enediol. And the process of shifting of the hydrogen from one atom to another carbon atom, which produce the enediols, is called as tautomerization or racemization also, or enolization. You can see here the glucose solution, glucose dissolved in the water, is you are adding it into the alkaline solution, some alkaline solution. Then there is a formation of glucose, fructose, and the mannose. So this is actually the tautomerization. They can change from one structure into the another structure. This is the same one, the enolization. The oxidation. When glucose oxidizes under proper conditions, the sugars may form monobasic aldonic acid, that is oxidation with the hydrobromous acid. We can also get the dibasic saccharic acids or alderic acid when glucose is treated with a concentrated nitric acid, or monobasic uronic acid when oxidized by some specific type of the enzymes. So these are all industrially important starting materials or the products. The formation of the aldonic acid, you can see here the glucose is there and then hydrobromous acid, it is forming the gluconic acid. Similarly with the nitric acid, the glucosaccharic acid. Similarly with the enzymatic varieties of reaction, it can form glucoric acid. Then sugar alcohol formation. Both aldoses and ketones may be reduced by enzymes to the corresponding polyhydroxy alcohols. The sugar alcohols function mainly as intermediates in the minor pathway of the carbohydrate metabolism. And some of these highly useful alcohols are following: the sorbitol, which I already mentioned in the second slide, or the mannitol, or dulicitol, or ribitol. So these are all finds applications in the industries. So the D-glucose we can convert into the D-sorbitol, D-mannose into mannitol, D-fructose into sorbitol, galactose into dulitol, ribose into ribitol. And medicinally, these are important, medical importance. Mannitol, it is used as in the osmotic diuretic to reduce the cerebral edema. Or sorbitol is used in the accumulates in the lenses of diabetic and produces the cataracts. Then one of the another important property which is exhibited by glucose, that is the oxygen formation. So when glucose molecule is treated with the phenylhydrazine, it forms a product which is called as yellowish to orange color product, which is called as oxygen. You can see here the glucose, which gives the its oxygen is called as glucose oxygen, and from the maltose it is called maltose ozone. And in the case of the lactose, it is nothing but the lactose ozone. So oxygen formed from the glucose, and they are the non-reducing sugars like sucrose. They cannot form the oxygen because the absence of the free carbonyl group in the case of the non-reducing sugar. So only the reducing sugars can undergo this oxygen formation. You can see here the glucose. It gives the initially there is excess of phenyl hydrazine which is required. That means two molecules of phenyl hydrazine will be reacting with one molecule of the glucose, and in between there is it forms a glucohydrazone, and then finally it forms the oxygen compound. Whether it is a D-glucose or it is a D-fructose or it's a D-mannose, the structure of the oxygen formed, it is the same, because the first two carbon atoms which are only the differs. And in the case of the phenyl, when it is reacting with the phenyl hydrazone, you have seen only the first carbon atom functional group and the second carbon atom functional group, only they are undergoing the reaction with the phenyl hydrazine. Since the rest third, fourth, fifth and sixth one are same, there is no any change in the chemical structure of these oxygens. These are actually the needle shaped, the physical nature of the different type of the oxygens which are found. Then there is the glycoside formation. When hydroxyl group on the anomeric carbon of a monosaccharide, it reacts with the an hydroxyl group of another carbohydrate or non-carbohydrate, which leads to the glycoside formation. So the bond between one monosaccharide to the another monosaccharide, which is nothing but the glycosidic bond. And there are two different type of the glycosidic bond. One is where oxygen is linked. You'll see both the example. And another one where the nitrogen atom which is involved. They are termed as oxygen glycosidic bond and nitrogen glycosidic bond respectively. You can see here oxygen type, first one. In the second one, you can see the between the nitrogen and this particular ribose sugar. So this is N type glycoside bond. Now, let us see what are the physiological importance of these glycosides molecules. Streptomycin, it's a antibiotic. It's a very popular antibiotic. So this is used as a drug for the treatment of the tuberculosis since the last several decades. That is basically it contains glycosidic bond, or it's a carbohydrate molecule, we can say. Then cardiac glycosides like digoxin and digitoxin. These are increases the muscle contraction and used for the treatment of the congestive heart failure. Then another one is anthracycline glycosides. Anthracycline glycosides like doxorubicin. So this is again another drug molecule, the carbohydrate-based drug molecule used for the treatment of varieties of cancers. Or oabane. So this is actually sodium and potassium ATPase and block the active transfer of the sodium. I may take another 5 to 6 minutes to complete the slide, another 5 minutes, and after that we'll have the interactions, if any. The derivatives of the monosaccharides. Some derivatives of the monosaccharides are phosphoric acid, ester of the monosaccharides, amino sugars, deoxy sugars, generally which are present in the acids, that is nucleic acids, sugar acids, sugar alcohols, etc. These are all different derivatives of the monosaccharides. So now the disaccharides, these are actually the term di. That means it is two. Here you can see the two friends are there, right? So that is nothing but the di refers to the two. So here two sugar molecules are chemically joined together. They are nothing but the disaccharides. So some of the best example is the table sugar itself we can take. That is sucrose as an example. And they have been classified into two categories. One is a reducing disaccharide and another one is non-reducing. Reducing examples are maltose and the lactose, whereas the non-reducing is regular table sugar. It's a non-reducing type. Maltose, and these contains the 2 moles of the or 2 molecules of the glucose units, and they are held together by alpha 1,4 glycosidic linkage. And it is one of the reducing sugar which has free functional group. You can see here it's a alpha because from the alpha D glucopyranose and alpha D glucose. So from this one, the first the glycosidic O bond, this is where it is coming in the lower direction. Please recollect in the Haworth representation, whenever it is on the right side, it should be presented on the lower side, and that is nothing but that will be considered as alpha. So this is alpha, and 1 and 4 because this one carbon atom of the first glucose molecule and fourth carbon atom of the second glucose molecule, that is 1 to 4, and there is a oxygen linkage which is a glycosidic bond. This is the structure of the maltose. Similarly, the lactose molecule, it is present in the milk sugar. It is linked by beta 1,4 glycosidic linkage. You can see here the beta. Alpha, if it would have been come in the lower direction from the first sugar galactose, then that would have been alpha. But here, just see the bond. It is moving in the upward and then coming down. So it's a beta, and first carbon atom to fourth carbon atom through the oxygen glycosidic linkage. So this is the structure of the lactose, or commonly present in the any milk. It is called as milk sugar. Sucrose, this is our table sugar. It is composed of glucose and the fructose molecule, and they are held together by alpha 1,2 glycosidic linkage. See here, alpha, because the glycosidic link from first molecule, it is coming in the downward direction. So it's alpha since it is in the lower direction, and 1 and 2. So first carbon atom of the glucose and second carbon atom of the fructose. So they have been held together by the glycosidic bond. Similarly, the isomaltose or the trehalose. So trehalose, this is actually one of the glucose molecule. In this one, two glucose molecules are held together by alpha 1 and 1 glycosidic linkage. And this is trehalose is commonly present in yeast, fungi, and like nothing but mushroom. So mushroom generally contains trehalose, and this also gives the mushrooms also gives the glucose molecule for us because it gives it has a trehalose as a disaccharide. So when it undergoes the hydrolysis, it gives two glucose molecules. The polysaccharides, which are nothing but the many, the starch is in one example. You take either the potato or the sweet potato or any other tubers, so they contain the starch, and in which about 15 to 20% is amylose, which is water soluble, and 80 to 85% is amylopectin, which is water insoluble. So only in the hot water it will undergo dissolution only to some extent. That is why the uh, the soup which is served very hot, it will be very thick. So after a few minutes, when it attains the normal temperature, by that time some amount of amylopectin also get dissolved. Because of that, it will be like a liquidy, or it's like a watery. Starch molecule, chemically amylose is a long unbranched chain of 200 to 1000 such D-glucose units are present. In case of amylopectin, there is a presence of the branches. So this is a structure of the amylopectin. You can see the presence of the branches. If it is a amylose, means only a straight chain structure. Dextrin, the partial hydrolyzed product of the starch by acids or the enzymes, which is known as dextrin. And starch is many of the bacteria also produce this dextrins. Starch is sequentially hydrolyzed through the different dextrins and finally to maltose and glucose. The various intermediates are soluble starch, amylodextrins, erythrodextrins, etc. And all dextrins have a free sugar groups, and they can allow, they can show some mild reducing property also. The glycogen, as I mentioned earlier, this is actually a reserved food in the animals, including the human being. So it's a major storage form of the carbohydrate in animals. So it is referred as animal starch. And it is present in high concentration in the liver, followed by muscles as well as the brain also. And the structure of the glycogen is similar to that of the amylopectin. As you have seen earlier, it is with the high branches which are present. The structure is similar to that. So this is the structure of the glycogen. You can see severe or high number of branches, large number of branches are present like that in the case of the amylopectin. And the cellulose, this is actually the chief constituent of plant cell wall. An unbranched polymer of glucose linked by beta 1,4 glycosidic linkage. Since humans lack the enzyme cellulase that can hydrolyze the beta 1,4 glycosidic linkage, cellulose cannot be digested and absorbed. So fortunately or unfortunately, we don't have the cellulase enzyme. Fortunately, if we were having the cellulose enzyme, uh, during the lunch hours, we can just have the any grass or any green leaves which are present in the garden. That is sufficient because it gives the cellulose, and the cellulose, if there is an enzyme, if we have the cellulose enzyme, that cellulose enzyme can cleave the cellulose into glucose molecules. But unfortunately, we don't have the cellulose enzyme. Because of that, we cannot digest the any cellulose rich food materials. Whereas the cattles or even the termites, they are blessed with this enzyme, that is the cellulase. Hence, they can easily, termites can eat on the food, eat on the any hardwood, because wood is basically, it's a made up of cellulose material itself. So it has an enzyme cellulase, so it can easily convert the cellulose into glucose molecule. The importance of cellulose is, it is not digested, has a great importance in the human nutrition. It is a major constituent of the fiber, the non-digestive carbohydrate. The functions of the dietary fiber, which includes decreasing the absorption of glucose and cholesterol from the intestine, increasing the bulk of the stool, aids in intestinal mobility, acts as a stool softener, prevent the constipation, etc. And it also reduces the incidence of CVD, colon cancer, diabetes, and many other health disorders. And there is a one more polysaccharide which is called as inulin. It's not insulin, inulin. It's a polymer of D-fructose. That means it's a starch. It's just like a starch, but it is not containing the glucose molecule, but it's a starch of the fructose molecule. And it is present in the roots of dahlia plant. ಡೇರೆ ಗಿಡ ಅಂತ ಏನು ಹೇಳ್ತೀವಿ ನಾವು ಕನ್ನಡದಲ್ಲಿ, ಡೇರೆ ಹೂವು, ಅದರ ಒಂದು ಬೇರನ್ನ ನೀವು ನೋಡಿರ್ಬೋದು. That actually contains this starch, the inulin as a starch compound, which is nothing but it's a polysaccharide of the D-fructose molecule. Then similarly, the mucopolysaccharides are also there. Then these are again few more examples. So I think I have taken 1 hour 5 minutes, 5 minutes more than the given timing. So if this is the timing for the question answer, I know most of you are in the YouTube line, you cannot interact, but those who are online, they can directly interact right now. Any of the questions related to this topic. And this topic is such a wide topic. Even at the post-graduation level, the carbohydrate itself can be studied as a separate elective paper. So I have covered only the very important and some of the basic things which are related to the chemistry of carbohydrates. Yeah. Over to KSTA studio.
Thank you, sir. Hello. Hello, sir.
Yes, sir. Yeah.
Thank you, sir.
Okay, thanks. Any questions?
ಡಿಯರ್ ಸ್ಟೂಡೆಂಟ್ಸ್, ಯಾವುದೇ ಕ್ವಶನ್ಸ್ ಇದ್ರು ಇವತ್ತಿನ ಟಾಪಿಕ್ ಮೇಲೆ ಯಾವುದೇ ಡೌಟ್ಸ್ ಆಗಲಿ, ಮತ್ತೆ ಇದಕ್ಕೆ ಈ ಒಂದು ಉಪನ್ಯಾಸದ ಟಾಪಿಕ್ ಸಂಬಂಧಪಟ್ಟಂತೆ ಯಾವುದೇ ಕ್ವಶನ್ಸ್ ಇದ್ರೂ ಕೂಡ ಈಗ ಸರ್ ನಿಮಗೋಸ್ಕರ ವೆಯ್ಟ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಸೊ ತಾವು ಕ್ವಶನ್ಸ್ ನ ಕೇಳುವಂತ ಟೈಮ್ ಇವಾಗ. ಸೊ ಇಂಟ್ರಾಕ್ಷನ್ ಆಗಿ ಏನೇ ಕ್ವಶನ್ಸ್ ಆಗಲಿ ಡೌಟ್ಸ್ ಆಗಲಿ ಸೊ ಸಾಲ್ವ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಸೊ ಯಾವುದೇ ಕ್ವಶನ್ಸ್ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಇಲ್ಲ ಸರ್, ಮಕ್ಕಳು ಯಾವ್ದು ಕೇಳ್ತಾ ಇಲ್ಲ.
Yeah, I know they are more in the YouTube. They are watching in the YouTube.
ಎಸ್ ಸರ್. ಹಾಗಾಗಿ ಸ್ವಲ್ಪ ಸೊ ನಾವು ಏನಾದ್ರು ಕ್ವಶನ್ಸ್ ಕಳ್ಸಿಕೊಟ್ಟದ್ದು ನನ್ನ ಲೆಟರ್ ಅನ್ನು ಐ ಸೆಂಟ್ ಥ್ರೂ ಮೇಲ್ ಸರ್.
Yeah, sure. That's fine, sir. You can communicate through the mail, and also you can share my phone number also. If they can also, if I'm free, I can answer them on the phone also whenever.
Sure,
I'm
sir.
free. I'm myself also free. Okay. So,
Okay, sir. Okay. Anyway, thank you, sir. It's an immense pleasure to thank you, Dr. Arun Isloor, sir. ಸೊ ತಾವು ಇವತ್ತು ಕಾರ್ಬೋಹೈಡ್ರೇಟ್ಸ್ ಬಗ್ಗೆ ಕೊಟ್ಟಂತ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವು ಕಾರ್ಬೋಹೈಡ್ರೇಟ್ಸ್ ಅಂದ್ರೆ ಏನು, ಅದ್ರ ಕ್ಲಾಸಿಫಿಕೇಶನ್ ಯಾವ ತರ ಇರುತ್ತೆ, ಮತ್ತೆ ನಮ್ಮ ದಿನನಿತ್ಯದ ಜೀವನದಲ್ಲಿ ಕಾರ್ಬೋಹೈಡ್ರೇಟ್ಸ್ ಯಾವ ರೀತಿ ನಾವು ಉಪಯೋಗಿಸ್ತಕ್ಕಂತ ಒಂದು ಸಂದರ್ಭದಲ್ಲಿ ಏನೇನು ಹಾಕಬಹುದು, ಮತ್ತೆ ಗ್ಲೂಕೋಸ್, ಫ್ರಕ್ಟೋಸ್ ಮತ್ತೆ ಮ್ಯಾನೋಸ್, ಈ ತರ ಹಲವಾರು ವಿಚಾರಗಳನ್ನ ಈ ಒಂದು ಉಪನ್ಯಾಸದ ಮೂಲಕ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. ಸೊ ಒನ್ಸ್ ಅಗೇನ್ ಐ thank you personally and on behalf of KSTA. Thank you, sir.
Thank you very much. I once again take this opportunity to thank Professor Ayyappan sir and Dr. Ramesh, as well as entire KSTA team, and also the audience who are going through the YouTube. So please come back to me for any further clarification related to this topic. Thank you one and all. Bye.
Thank you, sir. And also thanks to our academy President Professor Ayyappan sir, and also thanks to our Chief Executive Officer Dr. Ramesh sir, and our office colleagues and WebEx team. So thank you once again, sir.